I don't, for what it's worth.
It's an amino acid.
Interestingly,
Right. Many of these things have.
So it was very beneficial for...
My name is Matt Caberlin, and welcome to the Optispan podcast.
I watched this video, and there's also a corresponding sort of article written about this panel that happened in Aspen in June, so pretty recently. And there's a couple things that I just couldn't quite understand. And so I wanted to get your advice on it because it sounds promising. It sounds, pretty good. So just a bit of background. So the panel was Laura Deming, Kristen Fortney, and then Dr. Klausner.
Mm-hmm, right.
Okay. Are you familiar with those three people?
Yep.
Okay.
Yep. So I know Laura and Kristen personally. I've never met Rick Klausner, but I certainly know his background. Extremely prominent scientist at Altos, co-founder of Altos.
Okay. And what does Altos do again?
So, Altos is this company that was founded and funded largely by Jeff Bezos, but also by several others, primarily focused on, I think, what they would call rejuvenation technologies around epigenetic reprogramming. So using things like the Yamanaka factors to modify the epigenome and lead to at least cellular rejuvenation. And I think their goal is, tissue, organ, maybe whole animal rejuvenation. It's kind of funny because they are careful to state that they are not a longevity company, although I think many people recognize that is one of the areas that they're very interested in.
All right, Matt, so there's two things I wanted to get your opinion on about the video and the article. So the first one was the Spanish study, I believe it's in Barcelona, about organ transplants in mice. And the second one was Yamanaka factors and kind of what that is. And
sure,
I just don't know anything about it.
Sounds good.
All right, let's get into it. So I'm going to read a quote from the video/article. So he's talking about, we've been doing these experiments with the transplant team at Barcelona, where we remove a kidney from different animals. And now we're preparing to do this in the clinic. You take an old kidney and you transplant it to a young rat versus transplanting a young kidney, and you see a tremendous difference in overall survival and kidney function. But when you take the old rat organ and we introduce these components that rejuvenate the programming cocktail, just for 45 minutes, they're exposed to it and they're able to survive as well, if not better, than the young organs that were transplanted. Does that make sense?
Sure, it does. Yeah. And so again, if I understood the way that it's described in the article correctly, what they're doing is they have young animals. Mm-hmm. Are these mice or rats? Does it say?
I've read mice, but that just said rats in the quote there.
Doesn't really matter, but let's just say rats. Okay, so you have young rats. You do an organ transplant where you either put a young kidney into the young rat or an old kidney into the young rat. And the outcome is that when you put an old kidney in, that has detrimental effects on the young rat, presumably shortens lifespan and probably has other negative effects on health, compared to if it's a young kidney. And so this is, very related in many ways to the heterochronic parabiosis kinds of experiments that we've covered before on the podcast, where if you take a young rodent, mouse or rat, and you surgically connect its circulatory system to an old animal, that leads to benefits for the old animal and detriments for the young animal. The idea that there are circulating factors that change with age that influence health outcomes and longevity. So I think what this is suggesting is that's true at the organ level as well, and specifically in this case, the kidney, that there are changes in the kidney with age that can get into the circulatory system and have effects on other tissues and organs. Now, they didn't actually say that. I'm speculating a little bit, but then I think the important part here is that if they treat the old kidney with Yamanaka factors, and we can talk about what those are, that prevents the detriment that goes along with transplanting an aged kidney into a young animal. And the hypothesis is that it does that because it is rejuvenating the state of the aged kidney so that the aged kidney is no longer giving off these negative factors, right? Okay, so how do the Yamanaka factors work? So just at a very sort of superficial level, the Yamanaka factors are 4 what are called transcription factors that were characterized by Dr. Yamanaka, that's where the name comes from, that regulate the epigenetic state of cells. And so what's been observed is that if you take differentiated aged cells and you express these Yamanaka factors, it will revert the epigenome to a youthful state. Okay, so what does that mean? So again, there's the DNA, which is the genome. Then there's the epigenome, which is the modifications on top of the DNA that control which genes get turned on, which genes get turned off, which genes get turned up, which genes get turned down. As a cell goes from a pluripotent state to a differentiated state, say it becomes a fibroblast or a myocyte, a heart cell, or a muscle cell, there are changes in the epigenome that determine which genes get turned up and turned down to cause that cell become a fibroblast or a heart cell or a muscle cell. And what the Yamanaka factors do is they reverse those changes. Okay, so that's the dedifferentiation. It goes back to a pluripotent state. With aging, there are also changes in the epigenome, and the Yamanaka factors can reverse those as well. And so the hypothesis is the reason this works is because when you take an old kidney, and presumably this would work on other organs, but this is what they did with the kidney, and you treat it with the Yamanaka factors, you are reversing the epigenetic state to a youthful state. And then when you put that kidney back into the young animal, it's not detrimental anymore. So that I think is the context for this experiment. And hopefully I described what the article said accurately.
Okay, so you mentioned a rejuvenating cocktail that he's referring to Yamanaka factors. Okay.
Well, or some variation of those, but it's going to be some variation. It may not be the specific 4 Yamanaka factors that were originally characterized, but it's going to be related in some very close way.
He mentions Rejuvent a few times. Is that the same alpha-ketoglutarate that we've talked about in
No,
previous?
different. Completely unrelated.
He's just using that word. Okay.
Maybe that's what they call it internally. I don't know.
Okay, that's good to know. That's one thing that I was confused. I didn't know if that was the cocktail he was referring to. Was that?
So this has nothing to do with alpha-ketoglutarate at all.
Okay, good. All right. Well, let's jump to the video. I want to get your opinion on it.
Rick, you want to weigh in?
I'll take an experiment that we've done in Spain, which is a very great transplant center. So if you take old kidneys and you transplant them into young people, they don't do nearly as well as if you transplant young kidneys. But organ donors are getting older and older. And so we've been doing these experiments with the transplant
So this is interesting.
at
So
Barcelona.
what he's saying here is that in humans, organ transplant patients, if the kidney donor is older, the likelihood of a poor outcome is greater, right? So this is setting the stage for that mouse experiment we were just talking about. There's some evidence in people that the age of the organ donor can influence the likelihood of a positive or negative outcome in the recipient. And again, consistent with the idea that either the function of that organ itself or factors that the organ is giving off can have negative influences on the health outcome in the recipient.
So it seems like the main thing they're trying to solve is improving organ transplants. And if longevity is just sort of a benefit from that, which is why he's here talking about it.
That certainly could be the case, that in this case, the use case for this reprogramming technology would be to improve the health of the transplanted organ. So if the donor is older, you could imagine treating the donated organ with the cocktail, Rejuvent, I guess is what they're calling it. And then that would lead to a better outcome potentially for the recipient. Yeah, that's certainly a reasonable use case. And right, anything we learn about longevity or any effect it has on longevity of the recipient is a side effect, positive side
a bonus.
Effect. Yeah. I mean, interesting, just sort of personal anecdote here. So my father-in-law had a heart transplant in 2000, right? So 24 years ago now. And he was 65 at the time, and the donor was in, I think, his early 20s. So again, a young organ going into an older recipient, and he's still alive. So, N of one, he's sort of the poster child for a positive outcome from an organ transplant, heart transplant in this case.
But he's alluding to that that's rare to have such a younger heart put in. Most of the time it's...
I think what he's suggesting is that as the demographic changes worldwide really are happening towards an older population, we're seeing more and more aged donors for these sorts of organ transplant operations.
At Barcelona, where we remove a kidney from animals, different animals. Now we're preparing to do this in the clinic. You take an old kidney and you transplant it in a rat to a young rat versus a young kidney, and you see a tremendous difference in overall survival and kidney function. But when we take the old rat organ and we introduce these components that rejuvenate, this reprogramming cocktail, just for 45 minutes they're exposed to it, and then they survive as well, if not better, than the young organs that are transplanted. So it may well be with these types of creating cellular organs that are people doing, it may well be that we still want to make sure that we maintain the most healthy state of the cells. And I think, one possibility of that will be reprogramming.
So it's interesting. I mean, he didn't actually say what the reprogramming cocktail is, right? So I was working under the assumption it was the genetic cocktail, right, where you express these Yamanaka factors. I still think that's probably what they're doing, but it is possible that it's a chemical. People now have started to find small molecules that can mimic the Yamanaka factors, and it is possible it's a chemical cocktail as well.
Maybe I could just describe mice for a second, because we talk about mice, if that's okay.
Absolutely.
I mean, and Kristen said this, we all use mice, as an entry into the clinic, and we know how often that doesn't, and there are many reasons for that. Mice are different than humans. But another reason is that often when we do that, what we're doing is we're building, quote, a model of a human disease in a mouse that mouse doesn't actually get or doesn't spontaneously get. But one of the interesting things about watching mice age is how much, in many, many ways, it looks like human aging. I mean, when you have really old mice in a cage, it's like a really bad nursing home.
This is really important. So this is a really, I think, good point that he's making. So again, just to reiterate what he's saying is that, many of the studies in cancer, Alzheimer's disease, heart disease are done in mice. And, people always talk about how we've cured cancer or cured heart disease in a mouse and it doesn't work in humans, right? So therefore mice are bad models. I don't think that's the case. I think the problem is that people engineer young mice to get what superficially looks like these age-related diseases instead of using aged mice. Biological aging seems to be very, very similar between mice and dogs and people. So we need to study these diseases in the context of the aged animals. We should be using aged mice. And in that case, the conservation is probably very high. My speculation is most of what works for biological aging in a mouse will have some impact on biological aging in people. Will it have the same impact in terms of magnitude of effect? Nobody knows. But in terms of hitting the network that underlies the biology of aging, I think it's very, very likely. So I think mice are actually probably pretty darn good models for human aging in the context of biological aging. It is a little bit ironic. This guy's a former director of the National Cancer Institute, where so much of this work that he's saying now, we're using the wrong models happens. That's probably partly why, from a relative resource expenditure perspective, we haven't been particularly good at solving cancer. It's nice to see that he's come around to recognizing the importance of aging in these age-related diseases. So that's good.
I want to get your opinion on what he says next, because he essentially talks about you see two mice and one's really young, active, and the other one seems older. So.
They don't explore. They're not curious. You try to teach them things and they really have trouble remembering. They lose weight. They don't have sex. Their fur gets sort of mangy and will get white. Not all of it, but they'll start having white. And we can take those mice, and with a single injection of this new approach to reprogramming built off the Yamanaka things,
so again, he doesn't actually say what it is, right? So the implication there is it's not only the Yamanaka factors, or not explicitly the Yamanaka factors, but it's closely related. So again, it could be genetic, meaning they would take a subset of the Yamanaka factors or some, combination of Yamanaka factors with other things and express those genes, or it could be chemical, meaning they have molecules that mimic the Yamanaka factors that they're treating the animals with. And so it's just not clear exactly what they're doing. But I think for the purposes of the conversation today, we can just sort of assume it's equivalent more or less to the Yamanaka factors. And it's transient. That's the other thing that I think is important to note, is they're doing it for a short period of time, not continuously inducing this reprogramming effect, throughout the rest of the life of the animals.
I think he's just trying to keep it high level or potential IP.
Yeah, I'm sure that there are, that they want to be careful not to give away any details that they're still, getting their IP wrapped around.
And you go, and after a few weeks, to me, it was, I'm very skeptical about science. Seeing these mice is extraordinary. They gain weight. Now their skin, if you biopsy it, looks like young skin. Old mice and old humans, you've all had kids. I assume many of you had kids. When they cut themselves when they're 6 months old, and you go back the next day, it's hard to find it. If I cut myself, you can probably find it for the rest of my life. It'll be a scar. Same thing with mice. You do a punch biopsy, and they scar. But in these mice that have been rejuvenated, they completely heal. They still die. Even though we keep adding the rejuvenate, try to rejuvenate, they still die. They die about 25% longer, but they still die. And that's really interesting. So
I mean, there's a couple interesting things there. So, I mean, one thing is, I've said it before, right? You really have to be careful about science on YouTube, right? Like, what actually does the data look like? This guy's a good scientist. I'm not suggesting that he's saying anything that's not true, but you do have to be careful. People get excited. Sometimes what they say exceeds what the actual data shows. So, like, for example, he implied that their wound healing goes completely back to that of a young animal. Maybe that's the case. That would be awesome if that was the case. Maybe it's an exaggeration. The 25%, I think also, this is kind of important. We really would like to see the actual data there, because, it's unclear that, does he mean a 25% increase in remaining life expectancy from the time that the treatment was done? Or does he mean a 25% increase in absolute lifespan? And those are very different things, right? It would be pretty impressive if you could get a 25% increase in absolute lifespan from a single treatment during middle age. That it's possible. That would be pretty impressive. If it's a 25% increase in remaining lifespan, that's nice to see, but it's less effective than other things that we know about. So I think we just have to wait and see the data. The one thing he said here that's interesting, which doesn't surprise me, although it's a little bit, I think, disappointing, and for people who want to believe that we're close to extreme life extension, should be a little bit concerning, that they don't seem to be able to get beyond that point, even from repeated treatments. At least that's what he implied here. So what does that mean? Does that mean that you're the best you can do is this 25% increase with epigenetic reprogramming? Or does it mean that they're still suboptimally epigenetic reprogramming? There are a lot of people who are sort of putting all their eggs in the epigenetic reprogramming basket, that's going to be the thing that really, changes the game in terms of longevity. If the best we can do with epigenetic reprogramming is 25%, that's still important, but it's not as good as caloric restriction. And so I think this is, maybe again, a little bit more cautionary evidence that epigenetic reprogramming itself may not be this holy grail that a lot of people are hoping for the longevity field.
Yeah, I wanted to ask you, how does 25% rank up compared to CR or rapamycin?
Yeah, so it's about the same as rapamycin. Again, nobody's dose optimized rapamycin, so we don't know what the best you could possibly do is, but it's probably about the same. And it's much less than caloric restriction, maybe half the magnitude of effect you could get from caloric restriction.
Yeah, he's about to say it, but I think he sort of alludes to the idea of he doesn't know why, but it seems like the mice just sort of die. Like they just sort of give up. And I had I'll play it. I want
Yeah.
him to say it for himself. It reminds me, I have a great grandpa who was a veteran POW, and he died on Veterans Day, and it seemed like he sort of just like chose that day, and from our point of view. But I don't know if that's what he's sort of getting at. There's sort of like,
I very much doubt that's what's happening in the mice. I suspect there is some underlying organ or tissue pathology that their treatment is not fixing, or it's just, imperfect at fixing the things that normally limit lifespan in mice. Again, it would take a very detailed sort of end-of-life pathology to answer that. I can say with rapamycin, it seems pretty clear that the tumor burden, at least in mice treated with rapamycin, with the exception of a few high-dose experiments, is comparable at time of death. It's just that they're living longer. So it's as if the normal age-related cancer progression has been delayed, but not completely stopped. And so, you really would have to do a full end-of-life pathology on the animals to answer that question of, what does tumor burden look like? What does kidney pathology look like? What does heart pathology look like? Go across all the tissues and organs and really try to answer that.
I remember I had a professor at Western talk about how kidneys get a bad reputation for being the cause of death when really they're fighting the longest. They're sort of the first one to give up, but they're the ones that are solving for other issues.
Yeah, well, and again, I mean, all of the organs and tissues are interconnected, right? So in different people, different things fail first, but if your kidneys are failing, that's going to have a negative impact on your other tissues and organs because you're going to have a lot more toxins floating around in your blood. If your circulatory system is failing, that's going to have a negative impact on all your other tissues and organs because they're not going to get as much oxygen as they should. So these are systems of interacting components, right? And, for many of them, whatever your weakest link is can be what causes you to die, obviously.
I see. So the kidney, they might need it to be replaced because it's working so hard to solve a different issue somewhere else down the chain.
This question about what it looks like we're doing is creating health span. The average lifespan does go up, not dramatically. I mean, 25% is pretty dramatic, I think, but no more than that. By the end of the summer, we'll know in about 1,000 mice, really in great detail.
That's a good number.
Why they die. I mean, because that's really an interesting thing. I mean,
this is what we were just talking about, right? So
it
sounds like they're going to do an end-of-life pathology on the mice and be able to hopefully address that. Yeah.
I'm guessing that's an expensive study.
Yeah, they've got lots of money, so it's not a big deal for them. But I mean, just to give context, I think the mouse interventions testing program, so the NIH interventions testing program, for each intervention has, somewhere between 150 and 200 animals per intervention. So yeah, that's a really nice size study.
But there is this phenomenon that people at the end of lives just sort of stop. And we don't understand that and how that relates to all the other things we've been talking about doing.
So as we wait...
That would have been the comment when I brought up my great-grandpa. We mentioned people sort of just stop. So I wanted to bring up, Andrew Steele did a tweet about this. I'm not sure if you saw that, but I know you recommended his book to the coaches. So he said, we need to see the data rather than just on-stage chat. But if this stands up, it's pretty cool results. And 1,000 mouse trial is exactly what we need to see more of in longevity science. That's what a few $1 billion of funding, which relatively isn't that much, can do. So.
Yeah, I agree. I mean, I think that's a accurate comment. Certainly, 1,000 mice, we can be pretty confident in that result if that's the size of the study. And we have to see the data. I think that's the point I was making earlier. The only thing I would suggest again is that, if it is the case that it's a 25% increase in lifespan from a single treatment, that's impressive. If it is also the case that they can't do any better than that from repeated treatments, we should be asking ourselves why and what does that mean?
Okay. Was there anything else about this subject you wanted to touch on?
No, I mean, I think, again, there's a lot of enthusiasm and excitement about the Yamanaka factors and epigenetic reprogramming in the context of possible very, very large effects on longevity. I think some of us, myself included, have tried to temper that enthusiasm and say we really need to see what the data looks like. We'll see what the data looks like.
Watching this, the first thing I thought of, at least this clip, is this somewhat similar to David Sinclair's work on rejuvenating, I believe it was mice's eyes with Yamanaka factors?
Similar conceptually, yes.
Okay.
So the idea is to reverse the epigenetic changes that have gone along with aging to potentially restore function. And so in that case, it was limited to the eye. In this case, it sounds like, again, I'm making an assumption here because I don't know if he actually explicitly said it. Sounds like this is the whole body, right?
Okay.
Because, I mean, it's kind of confusing because they started talking about kidneys and kidney transplants. I believe this experiment is treating the whole body with the rejuvenation cocktail.
Okay, so just a little end of the video bonus is there's a couple questions the host asked earlier in this. I wanted to get your answer to, and also I liked his answer as well. So to get your opinion on that.
I mean, hope springs eternal, which is, I'm sure, how the supplement industry survives. Everybody believes they should be able to take something that is going to work. I am sure that snake oil has been around since time immemorial, but how, as scientists, do you think people are supposed to navigate what is real, like a clinical trial, you partnering with Eli Lilly, that's real, versus the kinds of things that are advertised to us all the time? You know, you can't go on social media or Google longevity without getting hit up to take, dozens of different kinds of supplements. Yeah. Do you
want to answer that first? Or do you want to hear his answer first? Sure if you have
I think I have answered it in prior episodes, right? I mean, I think there's a lot of noise and very little there's almost nothing that has been proven in the longevity supplement world, and very little where there's strong evidence for beneficial effects. And we've ranked them, so I'll refer people to that episode if they want to know my opinion on this topic.
Let's just comment about, we've all talked about this, about a lot of this comes from mouse studies where you give something to a mice and they live 25% longer, maybe. And it's very impressive to see that. A good example is caloric restriction.
So let's stop for a second, because I think I'm interested to see what he says about caloric restriction. But when it comes to supplements, what he just said there, he didn't explicitly say it about supplements, but it's not accurate, right? So there is this perception that a lot of these supplements that people are peddling have been shown to have robust longevity effects in mice. He threw out 25%. That's just not true. Almost none of them, if any, have had a 25% effect on lifespan in mice. And most of the stuff people are selling, if it at one point looked like it had a positive effect on lifespan in mice, has not been reproducible, right? So just look at the NAD precursors. So it is not the case that there's a bunch of stuff that has been reproducibly shown to have a large effect on lifespan in mice, and that's the evidence for why people should take it. In fact, there's very little that has been reproducibly shown to have a positive effect on lifespan in mice. Rapamycin being one, of course, which we talk about a lot, caloric restriction being another. And so we'll see where they go with the caloric restriction conversation. I just think it's important for people to appreciate a lot of these supplement companies will make misleading or outright false claims about how their product has been shown to increase longevity. Maybe it did in one study and then it failed to be replicated, or maybe it never was shown to robustly increase longevity.
Anything else beyond CR and rapamycin that's been shown? Or I'm just curious, like,
there's several things we've talked about that have come out of the interventions testing program, which I think most people would believe is the gold standard for demonstrating longevity effects in mice. So yes, there are multiple compounds that have come out of the interventions testing program. Most of those that have the larger effects are FDA-approved drugs that require a prescription, not supplements. So things like 17-alpha estradiol or SGLT2 inhibitors or acarbose. Very little in the way of over-the-counter supplements that have been shown to have robust effects on longevity.
And you have an episode going over those, I believe. Yep. Yeah. So I'll link that in the description.
Caloric restriction. They live longer. But that's if you treat
not all mice.
Black 6 mice.
Yeah, very dependent.
And instead, if you take 30 different strains of mice, they're all mice, and you do the same thing, about a third of them live longer. A third of them don't live any longer, and a third of them die sooner. And so I would then ask, so which mice are we? And so
I think this is accurate. And I've made this point on other episodes in the podcast, right? That there is this interaction between genotype and response to caloric restriction. Now, again, I know this is a pretty superficial panel discussion. It's important. I think it is important to note that the experiment he's referring to, where they looked across, about 30 different lines of mice. Number one, they were all inbred, so that might be important. Number two, they only looked at one dose of caloric restriction. So I think it's a little bit, and I've said it before, so I'm guilty of this too. It's a little bit of an oversimplification to say that in response to caloric restriction, 1/3 have their lifespan shortened, 1/3 show no response, 1/3 have their lifespan extended. That was about true in this one study using one level of caloric restriction. I think a more likely way to interpret this, a more reasonable way to interpret this, is that individual genetic backgrounds will have a different optimal dose of caloric intake for longevity. And so, for the typical genetic background, maybe it's 25% less than ad libitum. For a different genetic background, it might be 40% less than ad libitum. And for the rare genetic backgrounds, it might be ad libitum, right? Ad libitum meaning eat as much as you want. So I think we just don't know whether or not it is the case that some genetic backgrounds are always going to be harmed by any level of caloric restriction. What we do know is that for a given caloric restriction protocol, there will be genotype dependent effects, and some individuals will be harmed, some are likely to benefit, and some will probably see no change in lifespan.
Yeah, I want to get your opinion on that, because I remember reading that, like, if you overfeed a chimp or a gorilla, they partition more of it to muscle. They stay relatively lean, where humans, the same amount, 10% increase in calories could lead to adipose storage. Like, we're more wired to store fat.
Yeah, I mean, certainly, and even within people, that's true, right? There are some individuals who are more likely to store excess calories as either visceral fat or subcutaneous fat, right? And so that even the partitioning within adipose is different based on genetics, and certainly the likelihood that if you are over-consuming calories, you're going to build muscle versus store it as fat is going to be genetically somewhat determined. So it absolutely makes sense that across species there would be these differences as well. I still, it's my understanding that even in non-human primates and in rhesus monkeys, obesity is associated with shorter lifespan, or overnutrition is associated with shorter lifespan, and caloric restriction is associated with longer lifespan and improved health span. So I don't think it's the case that even if that partitioning is a little bit different, that the effects on longevity are substantially different.
All right, man. Good to know.
It just goes back to that we have an extraordinary system of trying to figure out, it's hard, truth through these very well-constructed clinical trials. And it's hard because people really want to do something to improve their longevity and health, and I totally understand. But, there's precious little. My own sense is that, I don't take anything, but for whatever that's worth. But when you look at all the data, I think the data for humans about health span is exercise. I mean, and the counteracting data that I think is most impressive in humans is obesity as a type of accelerated aging phenomenon. And you see that at the cellular level.
Yeah. I mean, again, I think that's a reasonable sort of high level interpretation, right? That regular exercise certainly improves health span on average in humans and probably lifespan, and obesity accelerates many, many diseases of aging, and I would suggest probably accelerates the biological aging process itself. Now, again, we've sort of touched on this in the past on the podcast, and, question of if you think about exercise and healthy nutrition and sleep and, which is most important for longevity, I think we don't know, right? Again, they're all important. So, so I wouldn't want to. I don't think the take home from this is that exercise is the only thing that matters, and you don't have to worry about these other pillars, right? But clearly, it is the case that exercise is an important factor that can improve health span for most
They're all
people.
Legs to a bar stool.
Absolutely.
You get rid of one.
Yeah.
I remember the first time we spoke last year, I mentioned the more I've learned about this field of longevity, the more I'm happy that I went into exercise as a career choice originally.
Yeah.
I feel like I was drawn into it, and it happened to be the one that's the biggest mover.
Yeah. Yeah. Again, I kind of go back and forth. I might have even said in a prior episode that I kind of think that exercise is the most important, but I'm not sure. I'm really not sure. I think that they're all equally important, maybe, and intertwined. I think that's the thing that is worth recognizing, right? Is that these things are all interconnected, and so, and probably individual as well, which is going to have the biggest impact on healthspan going forward. It's going to be somewhat of an individual formula, but I think the important thing is that you're going to get the best effects if you focus on all of them instead of trying to only think about one.
Which is why I refer to the tier list video. They're on the same tier.
Yeah, exactly. Yeah. Right. All right. So it's kind of unfortunate. I think everything that you picked up on were quotes that Rick had. I don't know if he dominated the entire conversation or not, but I mean, Kristen and Laura are both brilliant, and so we should come back at some point and talk about what they talked about here, because I think this looks like it was a very interesting and informative panel discussion.
Yeah, I watched the whole video and I was really impressed with both of them. But Laura in particular, she's 3 years younger than me. She's impressive.
Yeah, absolutely.
All right, Matt. Well, thanks for your time.
Yeah, thanks, Nick. Hey, everyone. Thanks for watching this episode of the Optispan podcast. As always, if you have any questions or comments, please leave them below. If you're not yet a subscriber, hit that subscribe button, and we will see you next time.